So, okay, well, interesting. Okay, we'll get back to that in a second. Okay, I wouldn't necessarily say injection molded parts are actually very porous. Okay, there are a couple of things going on. That's reaction injection molding, actually. So we're gonna.
Sorry.
No. This is good. This is good. So for anyone who's right. Okay, so let's talk the first thing about Henry's law. Okay, is that's this property that dictates how pressure and temperature of a liquid dictate how much gas they can store. So if you have a soda and you shake it up and you put it in the sun, or whatever you call it, what do people we say soda in New Jersey, right? I grew up saying soda, right? But I also am from Florida, so a lot of people would say like cola or pop. Well, actually, I didn't know many people that said pop. I'm from the south of the south.
Pop is Ohio.
Pop is Ohio? Okay. So if you shake it up, all right, you agitate it, you're actually creating a lot of little kind of nucleation spots, like little micro bubbles, that they're inside, okay? And I put it outside, and I open the container. So I've heated it up, and I've created all these nucleation sites, and now I open the container. So I've decreased the pressure. So what does that mean? That means all these little micro bubbles are going to expand and explode, and that's what you see. And you know, those people who do the Diet Coke Mentos experiments, right? The Mentos somehow behaves in the sugar. I don't know how it works, but it becomes kind of like a nucleation creator, a nucleation bubble nucleator, and that's what causes a lot of explosion. All right. So injection molding, though, it goes against Henry's law, right? You are And except for one thing, I mean, you've got a lot of temperature, right? So it's hot, but you're pressurizing the living daylights out of it so you can actually dissolve the bubbles in. And if you look at what's happening with the bubbles dissolving, it's very fascinating because you have a bubble in a liquid. So yes, it's going to want to get smaller, okay? But what actually happens is that you have a high pressure, and because these bubbles are getting smaller and smaller, you have a smaller radius, which leads to a higher radius of curvature, and then through something called the Laplace-Young relationship, curvature means there's pressure. You guys just did pressure vessels, right? I'm sorry I missed it. It's one of my favorite topics. But what we learned, right, that there's a relationship between the pressure, right, and the stress. So the pressure, as I squish these bubbles, there actually ends up being a higher pressure because of the curvature and because of the same equations that we discussed for stress. That's surface tension, right? Sigma essentially becomes surface tension instead of, because its surface tension is joules per area, right? Or it's actually newtons per meter, okay? So anyway, you have this surface tension that causes there to be a even a higher pressure, okay? Which means if there's a higher pressure by Henry's law, the inner surface of the bubble can hold more dissolved air in it than the surrounding liquid. So that means you have a gradient in concentration, right? So in the wall of the bubble, when you pressurize it, in the wall, there's a lot of dissolved air in that area, and that means that it wants to spread into the rest of the liquid. So you end up having diffusion carrying the air from inside the bubble to the surrounding liquid, dissolved at this point, and that's why the bubbles dissolve. So who was it, Kira, or was it Andrew? I don't know. One of you said something about it just goes into the bubbles dissolve. Was it Shane? I don't know. It goes into the liquid. So that's one of the reasons injection molding does that. But it's actually related to this bubble business that we've been talking about. We can think of the sigma that we've been talking about as being kind of equivalent to a surface tension. And a liquid has at a liquid air interface or at a liquid liquid interface, that is liquid air in the case of a bubble, right? You're going to have that surface tension, which actually causes there to be a higher concentration if there's curvature of air dissolved in that region. So anyway, thank you for humoring me. Oh, porous material. Okay, so why would you want porosity in your material?
Weight savings.
Yeah, weight savings. There's what else?
Insulation.
Yeah, insulation, right? Because air is an awesome insulator as long as it's not advecting, convecting, right, or moving around. So that's why we put fiberglass in walls, right? So that we can have nice air in there, but it's not moving, and we have convection, right? It's also good for bumpers on cars. Okay, so you create these materials that can absorb energy, and then you avoid having some of the accidents that you would have. So I'm not sure exactly which processes they use, but I think many of the bumpers that you see, at least back in the 80s, 90s, you had a lot of bumpers that were made out of a polyurethane foam on the inside. You know, they have a hard shell on the outside, but they have polyurethane on the inside. And this material has all these bubbles in it and absorbs energy, and the way they do it is a process called reaction injection molding. So they bring, just like the silicones we've talked about, are thermosets, where they kind of go one way. You heat them up and they cure. With reaction injection molding, you bring in a curing agent and you bring in a base and you heat it up quickly to get it to cure, but you kind of shoot it into the mold, and when it does that, it becomes like bubbly, it reacts, and you kind of try to control that morphology to get a nice shock absorbing material. So usually, like if you're thinking of toothbrushes, okay, those are injection molded, and those are often very smooth. Okay, so they don't usually have the porosity inside, and that's because they're trying to take care of the bubbles. But they do fun things right now. They have like these rubbery, nice, cushiony things that they add. I'm not exactly sure how they bind all those together. Okay, but the core, like the stereotypical, if there is a stereotypical, the conventional toothbrush is just a piece of plastic. Okay. All right. Well, today we are going to continue our discussion of different loads. This session is intense. Okay. Hopefully, I know the ring problems are a little bit tricky with the pressure vessels, but I like pressure vessels because it's like a nice little, how do you say it, discussion that goes off. It's standard for mechanics and materials classes to talk about pressure vessels, okay? And there are ASTM standards involved with them, and I think there are ASME standards as well, okay, that I should know this, don't quote me on that, but yes, no, they're ASME standards. But we very much want to make sure that we design systems that do not explode, okay? And so now you have some ideas. If it's a cylindrical pressure vessel, which stress do you care about more? The hoop, there it is, right? All right, that's the one. And what's its relation to the axial stress? Double, right? It's PR over T versus PR over 2T, okay? And you saw the derivations to be able to do that. So now we're going to think about how we look at systems that have the different types of loading we've been talking about in the class. And part one, we'll be talking about the different types of loadings. And some of this will be a review. And then part two, we'll talk about how we do superposition with the normal loads. So what are the normal loads? Those are like, the axial stresses. So you could imagine, I don't think I have this example in this particular session, but you could imagine a pressure vessel that's got pressure on the inside, and somehow I've got these clamps that I attach to either side. I don't know why I would do this, and I start pulling it apart. Okay, so now I've got if it's positive pressure on the inside, right? I've got a axial stress, all right, that PR over 2T axially, and I'm pulling it apart, and that's going to be F over A, right? Where A is the area of the annulus, annular cross section, right? Of course, where there's no material in the middle, it's not, where there's air on the inside, it's not handling that stress. So, you could imagine adding the PR over 2T plus the axial stress that I'm pulling with, okay? Or if I'm compressing it, that's a bad idea, okay? If I'm compressing it at the same time, it's not a horrible idea, it's just, why, unless I'm if I had to grab it and I'm moving it, but you don't want to apply a lot of force, or you don't want to apply vacuum to a pressure vessel. Why? Why do you think?
So it increases the stress.
Well, so let's say I've got internal pressure and I'm like, whatever, right? And I then push from the inside, or push on the outside, inward, right? That axial stress, I could maybe get it to go to 0, right? Because stress, it's in tension from the pressure, but now I'm compressing it, right? So at least in that direction, I've still got hoop, right? It's not helping with the hoop stress, right? But it's like, oh, I'm decreasing. But why is that a problem? I'm decreasing the stress. Isn't that a good thing? Yes,
You're
here.
just decreasing it this way and not this way?
Okay, well, so the hoop stress, right? Yes, I'm not changing the hoop stress, but why is it a problem? What happens if you take a soda can and what's the difference between stepping on, an empty soda can that's open, right? What happens if you step on it?
It's
It's
gonna crush.
gonna crush, huh? What do you say, Isaac? It's gonna crash, right? That's buckling, right? So we don't talk about buckling in this class. So a lot of times in mechanics and materials I do, but we don't. But buckling, yes, is a big problem that we'll quantify, at least for columns in the next class in DMC. But it's complicated in other structures with these pressure vessels, for example. But that's where you can use finite element, or you could look in a textbook and have analytical solutions. I was just walking by, so there must be somebody doing linear algebra. They're talking about eigenvalues and eigenvectors, and it has to do with, we don't do this at the undergraduate level, maybe some places. Actually, when I was an undergrad, they talked about this a little bit, but not in this context. Actually, if you take vibrations, you should talk about this. And you're like, what, vibrations, what does that have to do with this? Well, you figure out what the resonant modes are, which are kind of akin to the buckling modes, all right, of a structure. And so if you have enough force that kind of excites these modes of buckling, then you're going to have catastrophic failure. Okay. So pressure vessels, try not to apply vacuum to them. Of course, we have lots of things that have to have vacuum in them. So then, don't do thin-walled pressure vessels. I guess I should say that way. Thin-walled pressure vessels are not appropriate for vacuum, okay? Because they will implode, right? There are lots of, I'm sure if we look on YouTube, we find lots of experiments with people, imploding aluminum cans. All right. Okay, so after we discuss the superposition of normal loads, we will discuss the superposition of shear loads. And then we'll talk about what happens when you have both shear and normal loads. Okay. What are the types of loading that we've covered in this course? What do you all think? What do you think? What are some of the types of loads? Sure, Andrew.
Distributed load?
Yes. Well, okay, so distributed load, yeah, good. All right, so yes, we have distributed loads. Let me rephrase my question, because I didn't rephrase it well. What are the types of structures that we've analyzed and loaded. Yes.
Cantilevers?
So cantilever beams now, we're experts in the beams, yes. And beams, whether they're cantilevered or not. Yeah, what are some of the others? Rods, shafts, rods, yes, okay. Others? Yes?
Bars.
Bars, and then the last one is pressure vessels, we just talked about, right? Okay, those are pretty much the ones that we've talked about. Okay, so you have your normal force, and let me just make a comment. Okay, so you got your exams back. Please feel free to talk to me about them. I was a little surprised by some of the results, okay? And just like some of these things that we're talking about, they're review, and we have another exam coming up on Monday, okay? The difference between stress and strain is critical, okay? So please, if you're not using units, please use your units, okay? I think those of you who saw it in the exam, you got some of the feedback on different things, but maybe I didn't verbally write things, they just give a number. Okay, but just some tips. Please use units. If it's asking for a stress, all right, it's got to be some type of force over area. All right, it has to. If it's asking for a strain, it's going to be dimensionless. Okay, so just a couple of things there. All right, I guess I'll probably release something, but it was kind of. I haven't done the distribution chart, but it was kind of split. Not many people were right in the middle. It was like you kind of got it, or it was not. It was just like I was like, whoa, what's going on here? So I am concerned. Okay, I am concerned, and if you are concerned, we should have a conversation because we still have 2 more exams to go. Okay. And then tomorrow we're going to have a review. Tomorrow we'll have. If you desire, you can be here for 4 hours tomorrow. If you don't desire to be here at it's optional, completely optional, and we'll record this stuff. Okay, but feel free to come in an hour before if that works for your schedule or whatnot. And I'm hoping that maybe I'll be able to repeat myself a little bit on different principles, okay, over that time. But I am concerned. About like what I saw in some cases. Okay.
You said the review tomorrow starting at 11.
Yeah. But I don't think it's going to be me talking, like just talking. I'm going to be feeding off of you all, right? So come with questions, and then I'll try to answer them. And that's kind of the name of the game. Like I'm starting to see the group me starting to get populated, right? It's like if you have a question about it, there's a chance. Like when there was 100 people in the class, it was probably 0.01% chance that someone else, there was no one else that had that same question, right? Here, I know it's a smaller crowd, but there's still probably, like a 70% chance that, someone else has that same question. And then, you're helping each other out. What I've seen is completely appropriate. You can share your work over the group me, you can help each other out. You can say, hey, this is where I found, some help on this question, and, so anyway, that's the way we work. I work, right? It's hard for me to know exactly what you're thinking, so ask questions and then we'll get through it, right? And then I don't know, this is the last little thing, some people, we all learn differently, right? And there's controversy about, if there really are different, methods of learning, but we all learn, we all have our different styles. And so, some people will do really well in some things and others not. So again, if I think I've told you before, I love taking classes with friends, especially the friends that would get the stuff right on exams that I would get wrong, and I would be able to get stuff right that they would get wrong, right? And so those are the best study partners. Okay, so shear force, all right, yes, and that can happen through beams and happen just through the shafts and the torsion. All right. We have here's torsion right there, okay, and then we have the thin wall pressure vessels. So from this slide, and that's another thing I'll say is that some of the people who did the best on the exam, their formula sheets were very sparse. okay? So, you know, there are actually only a few equations, right? It's a matter of applying what's given, right? And I know I hope I'm not becoming. I know we're all going through a lot. There's a lot going on, right? So I don't want to be like this. I was a little concerned. Okay, so pretty much, yeah. You want to make sure you have all these types of loading on your sheets, and these are kind of the pillars of what we're going to do from here. Okay, and so if you have questions like, oh, I don't really get this like relationship between bending stress and bending moment, you know, let's try to resolve those. Yes.
Are we gonna get our formula sheets back?
Yes. In fact, I'll make sure I bring them tomorrow. I haven't. If you want, you can get it today. I have it in the office. Okay. I'm sorry, I didn't bring them today. But I have the hard copies. And yes, I know you saw. I scanned everyone's exams, right? And I sent them back, and they're like all yellow, right? That's like, you know, dark hotel room. Like, I don't know. You know, I'm sure there's some way to make them look better. But it's like I could read them. You can read them. Not the most beautiful scans, but you know, that's how it goes. All right. And then this is also review, right? So what do we talked about how if we have a bar under some type of force, under some type of load that's axial, right? We can think about the amount of stress that they can handle, and that by changing the diameter, okay, then we can essentially increase the amount of load it can handle, right? And that goes with the diameter squared because it's cross-sectional area. Yes. Oh my goodness. This was another thing, right? I told you that I get confused about D equals 2R. So do you. Okay? That's what I saw as well, all right? So please, diameter, right, is twice the radius. And I know it's a little bit tricky. There are little nuances in there. This is important. And again, it's helpful to keep track of the units. And we talked before about torsional loading of a shaft, right? And we've said how the supportable load scales with diameter to the third power. And now we know why that is, because of the College of New Jersey. TC over J. Or tau. Tau is equal to TC over J. TC and J. Okay. So we'll talk more soon about criteria for failure, and there are a bunch of different criteria that we'll look at. Well, 4 primarily, but more or less you have this idea that there's a yield strength, and there's also something we think of as a shear strength. Okay, and we want to make sure that our shear stresses or our normal stresses are less. Again, this slide is from I think maybe session 1, except for that little addendum about the shear stress there, right? This is also something that we've covered previously, and now we know that sigma equals negative my over I, right? And that's less than the shear, that's less than the yield strength of the material. And we can calculate out what the maximum bending stress is, and you're like, well, you didn't include the transverse shear strength or the transverse shear stress. That's true. Why? Because as we discussed, or as you hopefully you saw in the videos, bending stress dominates in beams as long as the beams are long. Okay. Remember we talked about double shear, and like this idea that shear stress in a beam that is, well, a quote beam that is transversely loaded is not going to be large until it's really narrow. Okay? So we typically just think about this, but you're going to be responsible, and we're going to talk about in the next little bit about what the transverse shear stress looks like, even though its magnitude may end up in practice being smaller. When we talk about combined loading, we say, hey, what are the shear stresses? We're still responsible for knowing what the shear stress is associated with a beam. Okay? And then we've talked about superposition before, right? Where you have different forces, or even two different forces, but maybe of different magnitudes at the same location that you can add up with each other, or maybe they're in different locations. Okay, maybe they're associated with an indeterminate system, right? Where you break it, or we first break a wall off, and we look at what's happening, and then we put it back on. Okay, and that was also right. At least the way I did it. People did different things on the exam, but the way I looked at that problem, this was 2B, I think. I looked at it as essentially a superposition problem. Okay. All right, so what do we do with forces and stresses? And, first off, I ask the rhetorical question, do forces and stresses have the same units? No. So can you add a force to a stress? No. Okay? So that's maybe, I don't know, maybe it needs to be said, maybe it doesn't, right? Can you add the effects of forces to each other? Yes, that being what's happening to the state of stress, right? Can you add a contribution, right, from some type of normal force? And I'll show you, you can have normal forces, as we'll see here, acting on a system, right? Beams, for example, that's pretty much the primary example, right? Which do create shear stresses. Okay? And those shear stresses, right, can then add to like a shear stress that might be caused by a torque or some other thing, right? Or a moment. So we want to make sure that we are adding stresses to stresses. Do not add normal stresses to shear stresses. Even though they do have the same units, all right? But we're going to essentially be populating those tensors. Okay, remember that the tensors, okay, look something like this, where you have the normal components along the main diagonal, right? And then we start doing things where we look at these other stresses, but these we don't write typically as sigmas, we write them as tau. Okay, and so you can populate them. So even that maybe that's another point I should bring up. I don't add a sigma x to sigma y either, right? They are in different directions. So don't add shear stresses to normal stresses. Don't add shear stresses that are not in the same direction to each other. Don't add normal stresses that are not in the same direction to each other either. Okay, and then we're going to make some assumptions for this class. One, the material is homogeneous. Okay, or maybe you like homogeneous milk. I don't know, but the material is uniform. You can take a class where it's not uniform. But that's more of a graduate level thing. Material has a linear elastic modulus, boom, and deformations are small. Okay. What happens, the classic example with deformations not being small is something like this, right? So like, that's a large deformation, and now you have to ask yourself the question, is the force still acting vertically, or did the force track and was it acting normal to the surface? Okay? So with large deformations, you start to get into issues. I mean, people talk, anytime that we can't explain something nicely, we say, oh, there are nonlinearities involved, right? Yes, there are nonlinearities involved because there are sines and cosines involved here, right? That's, as much as we love the trigonometric functions, as soon as we start introducing them, that means we're no longer linear. But we often use small angle approximations, or we highlight some, small perturbation about some angle which then means that we can approximate sine and cosine appropriately, you know, and sine theta obviously, right, will be equal to theta, or approximately equal to theta. Anyway, so we want to keep the deformation small. What is our procedure? We're going to, what? Section the material, okay? And typically that means we take a slice and we're trying to look at surfaces that have stress coming out of it or stress along it, okay? That would, you know, if it's along it, it's a shear stress, right? If it's coming out of it, that's going to be a normal stress. We're going to be determining the normal and shear force components, okay, along with the bending and torsional moment components, okay? And, you know, this won't be a big thing that we emphasize too much, but unless you're doing transverse shear stress calculations, but we're thinking about these forces and stresses and moments acting through the centroids of these surfaces. Okay. We can then determine the individual normal and shear stresses for each type of loading. Okay, so yeah, there are a lot of different types. We just went through that figure, or that slide at the beginning, right? Where you have the normal forces that are leading to normal stresses. You have shear forces that could be resulting in shear stresses with transverse loading of a beam. Bending moments, which could be leading to bending stresses in a beam. You have torsion on a shaft, that's shear stress, right, and thin wall pressure vessels, right? So it's, if you want to approach this from like a very algorithmic perspective, these steps are not bad, okay? Because you're like, oh, is there a normal? Are there normal? You got to figure out what are the normal stresses and what are the shear stresses. And in order to do that, you got to go back to what are the loadings and what is the structure. Okay, and we can add the normal components of stress to each other, as long as they're in the same direction. All right, and we can add the shear components of stress to each other, as long as they have the same subscripts. Okay, and we can then also show how these things are going to vary as we take multiple slices of our structure. Okay. Any questions on this? Any thoughts? Any inspirations? Yes?
What exactly did you mean by you can populate the stress of tau, if I was listening to that correctly?
All right, so the state of stress at a location has 6 parameters, right? Sigma x, sigma y, sigma z. Tau xy, tau xz, tau yz. For nice, homogeneous material, right? Because the off-diagonal terms is symmetric and is symmetric. So all I'm saying is that when they say, hey, here's a slice, or here is a point on a structure, tell me the state of stress. We've got to think these are all the possible options, right? And usually it's only like 1 or 2, right? So the rest are all going to be 0. For our intents and purposes. Okay, but yes, we're essentially trying to populate these tensors. Does that make sense?
I think so.
Okay? So it's like a big game of combinatorics or something. It's like these are all the combinations of things that I'm telling you, these are all the parameters that affect all the combinations of possible solutions. Our job is to then figure out which one of these combinations, or which combinations are the ones that are important. And usually it's only a couple. It's like the Wheel of Fortune, right? You gotta figure out which letters are important. That's really a bad analogy. I don't know why that came up, but I guess Wheel of Fortune has been in the news lately. Right? Past Jack retired? Yeah. Okay, and Vanna White is still going, right? Is that what I read? It's like, whoa. Okay, so a bending moment and an axial force might both contribute to normal stress. True or false? What do you all think? Okay, why do you say false? I said might. I didn't say always.
Ah. I was thinking might because moments usually contribute to torsional stress, right?
Do they? What about moments on the beam?
Oh, right.
Right? Sigma equals negative my over I.
Hmm.
Right? Remember that n is an internal bending moment, but it's reflective of, it could be reflective of either a normal force, a transverse force applied to the system, to the beam, or a moment being applied to the beam. Okay? But yeah, so this one is true. Okay? If I had said always, well, if now that you know me a little bit, you'd be like, oh yeah, he doesn't like superlatives. Okay, so that would be a false. Okay, a torque and a shear force might both contribute to a shear stress. What do you all think? Someone else, someone else.
I'm gonna go with true.
Okay, why? Why do you say that?
Because they could.
Yes, it could, because it has the word might. See, so now you use the opposite logic that I would use for superlative. Someone else want to help Eric? No, Eric, you don't need help, but someone else want to give an explanation. Someone else want to give an explanation. What is, so the thing is, and when I say might, what is an example where this could be true? Huh? Okay, so yeah, so absolutely right. Torque is most likely going, like, I mean, moment, yeah, torque, I mean, right, think shaft. Okay, let's think shaft. Alright, so I've got a shaft that's being twisted with a torque. Now, that's contributing shear stress. What about a shear force? That's what you don't, okay, well, whoa, okay, so hold on. Shear force, where have we talked about shear forces?
Internally.
Yeah, mostly internally, but we've talked about them in double shear now, okay, and in beams. So, but shear force typically, yes, is an internal construct. That's the V, all right? So, does a shear force contribute to a shear stress? You betcha, right? We said, or I remember that if we can figure out the average shear stress on a face on a beam internally, right? That's just that shear force divided by the cross-sectional area. Turns out that the average is not the max, all right, and it's not the min on a face of a beam, but we have relationships like 3/2 times the average shear stress that can help us figure out what the maximum shear stress is. And like, so 3/2 or 4/3, write those down. 3/2 times tau average, 4/3 times tau average. Know which geometries those are for. 3/2 is for the rectangular cross section. 4/3 is for the circular cross section. Because why? Why do I say that? Because then you don't have to do the whole V quit, all right? The VQ over IT to calculate the shear stress. If I say what's the maximum, you better hope that it's a rectangular cross section or a circular cross section, and then all you do is calculate the average shear stress and you multiply by 4/3 or 3/2. Okay, does that make sense? If it doesn't, please go back and watch the video of what I just said before Monday, and then go back to the notes. Was that beams 4, I think, on transverse shear stress and beams. Okay. Trying to make it easy. All right, so this is true. We describe the stresses within thin-walled pressure vessels as pairs of shear stresses. What do you think about that? It's like a vocab test, right? You're like, come on, what? Yes, Eric.
Say true.
Okay. So everyone says I can't hide my I'm not very good at lying.
Yeah, no, you were disappointed.
Yeah.
I have kids. I know the one.
All right.
hoop and then there's axial, but I didn't know if those are
So are those
considered shear stresses
Are they
or
shear
if you consider
stresses?
them pairs. I don't know.
well, are they? I mean, I say sigma 1, right, and sigma 2.
Mm-hmm.
Sigma always means
Sigma.
sigma in general means I mean, I just from sigma 1, 2, and sigma 2, 3, and sigma, but typically
Stress.
those are normal stresses.
Okay. All right.
All right. So shear stresses, we don't have any equations for shear stresses within low pressure vessels. Okay. Not yet. Not yet. We will talk about the equivalent shear stress in a thin wall pressure vessel, but we don't think of it in terms of pairs of shear stresses. Okay. Typically, we describe them in terms of normal stresses. We can convert them to an equivalent shear stress, but yeah, that's good. So this is false. Yes, what were you gonna say?
Are there not any shear stresses in thin wall pressure vessels because the whole thing is expanding at roughly the same rate, so the material isn't kind of rubbing against each other?
Okay, we will come back to this. We will think of equivalent shear stress, okay, because if it's a ductile material, like a lot of the metals we're thinking about, the reason it fails is actually because of shear stress, not because of normal stress, okay? But as we derived, right, we derived that these are normal stresses, meaning for the stresses we derived, for which we derived, they're coming out of things. All right, so we don't typically think, all right, so not pairs of shear stresses, but pairs of normal stresses. Okay, sigma 1 and sigma 2. And if it's a sphere, then it's all the whole thing, right? And if it's sphere, then there's no shear stress equivalent. Okay, at least not in the plane. There can be normal. There is in 3D. All right, we'll get into that later. Okay, we add bending stresses and shear stresses directly to create composite stresses. Isaac, you raised your finger, so I'm going to pick on you.
Alright, no, it's true.
Go with your first hunch. It's false, right? Because we can't add shear and normal stresses to each other. They're different types, okay? This is false. We'll talk about equivalency again later, but if you give me a signal x and you give me a tau xy, they're separate. Okay, I can't add them. That's what we're talking about populating the tensor, right? I gotta populate these different components. Okay. Okay, for a cantilever beam, the maximum supportable bending stress scales linearly with the base width of the beam. Someone else. Not someone else. Both of you.
Sorry.
Yes, Dylan.
True.
Yeah, it's true, right? This one's true. Okay, why do you say that, Dylan?
Because it is.
Yeah, so that's true, right? So we talked about BH cubed over 12, right? And so that's going to come out in the NY over I. So I being the BH cubed, right? And B is the width, right? So it's sigma is equal to essentially something proportional to 1 over the width, all right, from the mechanics. Okay, for a torsionally loaded cylindrical shaft, the maximum supportable shear stress scales with the radius cubed. What do you think, Matthew? Yeah, it is true. All right, and that's kind of for the same reason we discussed. Okay, is that we have a relationship for J now, right? Because we have TC over J, right? And then J is going to be C to the 4th, but there's a C in the numerator, so it ends up being. Okay. All right. I guess that was one of the questions for your homework. So now you got it. All right, superposition of normal loads. And normal loads, right? Remember, when I say loads, it's because I'm being vague. Right? It's like, the load. It could be a moment applied to it. It could be a force applied to it. It could be a pressure applied to it. Right? A load is just something that's going to cause some stress. So here is kind of an approach to doing this. We have an opportunity to use method of sections. So we section our object. Perpendicular to an axis at a point. All right, so sometimes the stress doesn't vary across the cross section, right? So like I've got a bar and I'm pulling it with a force. For our intents and purposes, when I take a slice through that bar, in reality there could be some differences near the edges and things, right? And we talked about boundary condition where the FEA, and you've got this thing happening where you've got Poisson effects, whatever at the constraint. But and so that in that case you're like, for our intents and purposes, the stress is the same across the entire face. But it's important to know where this this interrogation is happening. So you want to know a direction and you want to know a location. We want to determine the normal and shear force components, okay, along with bending and torsional moment components. And force should act through centroids and moments that should act about centroids. Okay, so this is, again, it's mostly for a beam, all right, that you're going to have these normal and shear force components. So bar will have this normal component, shaft will have some type of shear stress, but not a shear force associated with it. Okay. We're going to determine individual normal and shear stresses for each type of loading, right? So this is repeating each other, and we're going to add the normals to each other and add the shears to each other. Okay. Again, this is just repeating essentially that multiple choice question and what I said before. It's just so important. Okay. Please, it's like adding stress and strain to each other. Don't do it. Okay, just don't do it. Because they don't have the same units, they're very different concepts, right? Of course they're related to each other, but just they don't have the same units and doesn't make sense. Okay? So we had a bunch of different types of loads, right? And different types of stresses that we could create. Right? And if you go back in your head, do you remember which ones are the ones that contribute normal stresses? Yeah, take bars, that's the easy one. Right? What's the next one? Or what's another one? Which ones create normal stresses?
Pressure vessels.
Pressure vessels, those are normal stresses, right? What else?
Quick learner.
Huh? Quick learner, right? Thank you. Yes. Huh?
Beams.
Yeah, beams, right? So those are kind of the big three for this. Okay? That you have these bending moments, and you have the thin walled vessels, and you have the bars. Okay? That's it. Okay? For the at least for what we've discussed in this class, that's how you're going to have normal stresses. I guess I could say thermal. I mean, that's kind of in the bar category, right? But like, oh yeah, that was another thing that came up. Okay. If I heat a bar up and it's got no wall on the other end, all right, the stress inside of it is, like I got a bar, it's free on one end, I heat it up by 100 degrees Kelvin. Zero stress, right? Zero stress. I've got strain, but I've got no stress. Okay? When I constrain it, yes, I can then have a compressive stress. Okay, so yes, I could have had that. I could have added thermal here, as long as it's constrained thermal. Okay? And if Jumbo the elephant is sitting on a stool, right? First, if he's sitting on a stool and gravity is acting, right, the legs of that stool are going to be under loading, right? Because that's loading is a generic word, right? But they're going to be under compressive stress, okay? Because all those legs are compressing, okay? And that's the other thing. It's like before you say, I said stress. I did say compressive stress, but before you even think about it, right? Please just look at it in your mind. It's like, oh yeah, everything's going to be, the forces are going down, so it's just got to be compressive, okay? But anyway, then this is the thing that very few people, and maybe it's because I'm mean, I don't know. So I've got compressive stress. Now I heat up the legs, all right? So then that Jumbo the elephant goes back up to his original height. What is the stress in those legs?
Right, no.
No,
Strain is
no,
zero.
right?
Stress is
Right?
zero.
Did not people you read the okay,
I
you
read
read my
it.
comments, right? So like, no, because it's not. The Jumbo the elephant is heavy, but he's not a wall. All right. So he's still acting down on this system. Just imagine, right? It's like saying I take my table and I put it in a 40 degrees Celsius room, right? We change the temperature by 20 degrees. Is there still compressive stress on those legs? Absolutely. That's all I was asking, right? So maybe it was mean, right? But it's yes, there's still going to be compressive stress, and it hasn't changed. Okay. Jumbo the elephant may have moved up a little bit, but I didn't push him into the ceiling or anything, right? So he can't add any more. Okay. And just because the strain is zero doesn't mean the compressive stress is zero. Okay. Anyway, so let's take a look at this. Before we even do anything, no math. Okay, if this is positive, what is it inducing onto this structure? What kind of stress? If F app is positive, what kind of stress do I expect that to give inside the bar? Or inside the beam?
Normal stress.
Yeah, normal stress, and is it going to be compressive or tensile? Tensile, right? Because it's pulling it all apart. Okay, good. Now, a little bit trickier. Beam at point A, and like I could have said at point A and at point B, right? But I knew that it was just, that's across the entire thing. But now, location matters a little bit more, right? We care a little bit more about the real estate. Where I am at A, will M at apply a compressive stress or a tensile stress?
Compressive edit.
Right? It's going to be, so before you even do any math, just look at the thing and you're like, oh yeah, I'm making it smile by applying M at. And because it's smiling, the top, I can't even do it with my own face. I must not smile very much. I don't know. But like, anyway, the top is going to be in compression and the bottom is going to be in tension. Okay? All right, so now let's rock it out. Got to select the cross section, right? This is kind of step, that first step we were talking about. So there's a cross section. And it's probably not a bad idea to also do external loading on this system, right? So that we can figure out, okay, I do have an ML and an FL. These are, the loads due to the wall on the left side. The lowercase l is just means left for me. So I'm guessing that reaction moment from the wall is going to counteract the MF, so I've drawn it that way. It's a reaction moment, so that means I could have drawn it either way. Okay, and then I'll solve for it, but I've drawn it in a way such that I hope that ML will be positive if MF is positive. And then FL, right, that's the force of the wall acting on the beam, and that should be going to the left if FF is positive. Again, if I drew it the other direction, I could have. Okay, I could have drawn this the other direction. I could have drawn these reaction loads the other direction, but I chose to kind of pick them so that they would be positive, assuming these are positive. Okay, so I have FL is equal to FAP, and I have ML is equal to MAP. Now, let's take a look at the internal bending moment. So here, when I do the internal slice, I do have to keep track of my convention. My convention that I have, right, is that if I open and to the right, I have a V going down, I have M being counterclockwise. Okay. Now, one thing that may be a little bit different that we don't think about is that when I take the slice, I also have this normal end. Okay, so you'll see that in textbooks, and we'll see it here, that I can also draw a normal axial load. Again, we probably do that in statics. It's just usually we forget about it. But because I want everything to be in equilibrium, right, I have this FL over here on the left side. It's not a bad idea to draw it there as well. And because this is a superposition problem with normal stresses, I might as well figure out what the normal stress is associated with it, okay? So I have M equals MAP, and I have my N equals FL, and I have a V that I've got to calculate as well. Well, the internal shear force here is going to be 0. Why? Well, because there's no other force in the vertical direction. Okay, so that one's pretty straightforward. The internal normal force, like I said before, we have N is equal to FL is equal to FAP. Okay, and so now we can begin to think about a normal stress. There's one normal stress from N. What is it? It's normal stress to the N. Okay, well, yeah, so I have FAP, and then what else do I have to do? But that's not a stress. FAP is not a stress. Right? N is not a stress. N is a force. So I just have to divide by the cross section area, right? So I have sigma N is equal to sigma A is equal to sigma NB, and then it's just going to be N over A, or N over BH. Okay? Because it has a width B and a height H. Okay, now stress, okay, from the internal moment at A. So A is up here on the top side. So sigma MA, this is just using the definition, right? This is the bending formula. I got negative my over I. And you know, I don't think about this negative sign that much. I think about it like as an afterthought, like after I've calculated the magnitude, I come out, I look at the geometry, and I'm like, yeah, it's going to be under compression there, negative, okay? But it's nice that it does work out. Why? Well, look at this. Here's an internal M. If M is positive, right, which it is, then it's positive. What is Y? Y is half the thickness, right? Y max is where A is, right? So Y is going to be equal to H over 2. Well, thickness is also positive, okay? I, right? That's the pi over 4, or that's the BH cubed over 12. Sorry, it's not cylindrical. BH cubed over 12. So that's going to be positive. So in order for this to be compressive, like in order for the stress to be compressive at A, which we said at the very beginning of this problem, I gotta have a negative sign, and M is positive, Y is positive, I is positive, okay? But I would probably just calculate what the moment is, calculate out what the Y is, and then lump on a negative sign afterward, right? No one's gonna know, right? Because I can't see what you did, right? Just, you write it out and oh, it's gotta be negative, okay? And so that's what this result is. Now, if it's a variable result, then yeah, you gotta, if it's a numerical result, you can do what I said. If it's a variable result, then yeah, it's probably a better idea to have a negative sign. But again, the MF is positive, so again, I could just throw a negative sign on it. B is positive, H is positive, right? Okay, and then stress is at B is going to be, the bending stress is going to be exactly the same, right? But it's the opposite direction. And so we have a negative of a negative. And so that will end up being a positive. So right there, again, I could just kind of say, oh, I know what this is based on, I mean, it's symmetric and whatever, and it's going to be a positive. Any questions on this? Okay, so I still haven't quite answered the question. What am I missing? Well, I need the stresses, I need the normal stresses, okay, at A and B. So what do? We gotta do some addition, right? So let's look at the stress profile from N across the face. It's just coming out like that, pretty uniform. Okay? And what's the stress from M? Well, this one is got a little bit trickier profile, okay? But it looks something like this, right? Where with these diagrams, okay, it's a little bit, probably haven't described this super well, but you can think of this as being kind of a plot, right? Where this is now coming out as a positive stress and going in as a negative stress, okay? And so this is what the profile looks like. It's linear, right? Because M is constant, I is constant, and Y is varying, okay? So we had to look at what's happening at A. Here's A, and then we draw sigma A, we draw sigma A. And we also have it being the normal stress from F applied, okay, acting against, or you could think of the bending stress as acting against that normal stress of F, right? So we're saying that A is essentially right here, okay, at this location. And then at B, at the bottom, okay, we can say that, again, we have a normal stress, and this is going to be these two stresses acting synergistically. So 6M over BH squared and N over BH. Well, I mean, is it synergistic? Well, they add up to each other. Okay, that's nice. Okay, but where do I think it might have a higher probability of failing? Well, probably where the stress is higher, right? This magnitude most likely is going to be less than this magnitude, or I mean, I can change the signs, right? That could change things actually, So then, if MAP is negative, then I'm going to get that it's going to be more tension on the top than the bottom, right? But essentially, we're able to look at these equations, or use these relationships to be able to determine what the magnitude of the stresses are going to be, and we're adding normal stresses at a particular location to each other. Now you ask yourself, where is this element? What is this element? This element, the way it's drawn, I said I'm looking from the side, kind of. But this element could also be on the top surface. That would be fine, okay, and have that axial load coming out, right? So it's not super critical in this particular example, but it is something to keep in mind. Okay, whether I've like plastered on the side, or I'm looking at the top or the bottom. Okay? Either way, it's going to have the same exact stress. It's a normal stress. It's in the x direction. Okay. So let's look at another. Well, this is a problem actually. Okay, we won't do it exactly. but think about it for a second. How is that P creating stresses in the system at location A? Because that's what it's asking, right? And remember, this particular part of the session that we're having today is about just normal stresses. So, how is P influencing the normal stresses at A? Or normal stress, but I gave it away. The combined normal stress. Yes.
It's putting A in compression.
Okay, so one is, it doesn't matter where I apply P on that top surface, right? It's going to be compressing the, it's leading to some compressive force, right? So we have a normal stress, one normal stress, okay, and we'll call it 1, okay? That one is going to be like you just said, and I'm going to say, if P is a positive quantity, right, I'm going to say it's minus P over A. Does that make sense? Actually, I want to use a different, what is a better nomenclature? That's fine. We'll call it 1A, actually. Later on, it'll be clear why I'm doing this, but right now, okay. Now, what about its location? Does the location of where P is applied affect the state of stress at capital A? Okay, how so?
So if it's applied directly, like collinearly with A,
Like right around here? Oh, I see. Okay,
then it won't introduce any stress in like the Z direction or the Y direction. But if it's not, it might.
Okay. So, this is good. So, one question is, can it introduce a normal stress in Y or Z? I didn't really draw Z, but X cross Y would give us Z, which would be coming out. What do you all think? Can it be contributing to normal stress in that direction? Normal stress. No.
The way
I
you
would agree.
emphasize normal, it's no.
No. But could it be causing a shear stress? Well, that's interesting. Okay, also kind of a good review. Where is, this is kind of a beam, right? Can you have transverse shear stress on the outer surface of a beam? The way we've defined it is no, right? The maximum transverse shear stress is on the middle, on a neutral or longitudinal axis. A neutral plane, neutral axis, longitudinal axis, whatever you want to call it, right? That's where the transverse shear stress is going to be a max. So there's actually no shear stress here because of bending. That's just because of location, right? So, yeah, if it were in the middle, then we could think about a shear stress that it could be inducing because of bending, all right? I think you're also kind of thinking, well, if I do it like off axis, then, or if I was at the middle, maybe it's like almost like a double shear situation. That's not really what we're getting at here, okay? And so if it was like a shear, or you have a double shear or something, and maybe you could induce a shear force and a shear stress directly, but no, we're not really going for that, okay? In this case, we're thinking about how, and so we've eliminated this transverse shear stress, but also another thing to point out is that we're only asking about normal stress. Okay, so really we had to think about normal stress. So how does the location of P affect some normal stress, we'll call it 1B. Okay, so you've got one normal stress already, but I'm going to tell you that there's another normal stress. Let's call it 1B. Yes?
Is it due to like the moment that's created E times A?
Yeah, all right, okay, so let's bring out the bending formula, and we'll say that sigma 1b somehow magically is related to negative my over I. Okay? And then you start to think, oh, you know, if I move p right to, let's say, with a equals 0, right? If I move p to where a would be equal to 0, well, or the y equals a 0, let's say, okay? Or y equals 0, assuming y starts off at this kind of midline right here. Then I'd have no moment, right? That's what you're getting at, Andrew. But since it's off here, okay, I have a moment that's being applied. You can kind of see or almost feel that, right? It's going to try to twist. Like, which way is this going to smile? With where P is right now, which way is it going to smile?
It's going to be in compression, and on the other side it would be
In tension, right? Yeah, so it's kind of smiling like this. You know, like kind of like that, right? You can kind of just see that. So, again, we can kind of forget the signs. At least I kind of think of it. I try not to think about the signs of the moments too much, but I think about the what the net sign is. I can kind of think of it as you just said. It's like minus PA, and what's the y? The y is going to be another a. Do you see that? The way a is defined, it's half the thickness. All right, and then the I, right? I is going to be equal to BH cubed over 12. Well, guess what? The H is 2A. Right? So that's how we want to attack this particular problem. So the normal stress 1A is in compression. Normal stress 1B is also in compression. Right? So this is going to be a negative stress. Right? Any questions about that? Did I move a little quickly at the end? Okay. Right. So the superposed or the combined stress, normal stress, is going to be these things added to each other. Okay, let's go to part 3. Superposition of shear loads. All right, so this is obviously a little bit more confusing than normal stresses because, well, you've got a location and you've got a normal face, and then you've got a direction to think about. Okay, so it's just more confusing than normal loadings. But the general procedure, ad nauseum, section the material, determine the normal and shear force components. Then we're going to want to determine the individual normal and shear stresses. Okay, and we're going to add the normal components to each other and add the shear components to each other. Okay, and we're going to show the result. Okay. So, what are our possible sources of shear stress? Right, and so this is the other thing, right? What we showed, like maybe I should have emphasized this in the last one, right? We had a slide where we said these are all the possible normal stresses that you could induce. Right? It was bars, beams, and pressure vessels. And in that last example, the last question, we had bar and beam. Okay, it was serving as both of them. Okay, so now we're talking about superposition of shear stresses, and so this means that we got to think about, okay, what are our shear? How do we even get shear stresses? So we had to think in our minds, this is like, is that structure that the silly guy just drew, all right, because that's what you're going to do on Monday, or is that structure sitting out there, that tree, all right, or that side of the building, all right, or, you know, I don't know, some kid putting their foot on the fire hydrant right there and kicking it, you know, transverse to the shaft of the fire. We gotta be able to say, oh yeah, this is what the structure and the loading are going. How can we induce shear stresses, right? So essentially, we have beams, right, that can induce a shear stress, and that's because we have a shear force. I kind of like this drawing. I think it's actually one of my better ones, okay? Because what you see here is the V, which is what we drew in statics and what we've been drawing now. But if you start to look at the individual small elements on the face of this beam, what you have is an individual shear stress, or a shear stress with a different quantity depending on where it is along the surface. Okay, you can figure out that it's not just V. And we talked about, in this case, the max, which, you know, maybe is around here, right across the middle. That max for this rectangular cross section would be 3/2 times this average. This is the average. Well, in this case, this would be the average, okay? And so you can avoid doing all V quit, all right, by just knowing that I'm asking for where it's the max. So it's max along the neutral axis, okay, or along the longitudinal axis. And it's also important to note that for our intents and purposes, we assume that it only varies as a function of height or distance away, the y quantity, away from the neutral axis. So when y equals 0, that's when the shear stress is a max. Now another thing, you know, and I know you had to watch the videos of this because I wasn't here, is that this, if I take a block, so you see this block, or you see this little nice little shear stress right here, and maybe I should, this might be worth zooming in on it. If I take this little face here, it's really, this face is attached to an element. And this element is embedded in the beam. Okay, so I take a face, and I take like a little micro face of a slice of the beam, and then I look at the shear stress on that face. That, the way it's drawn right there, here, okay, this can't be in equilibrium. Right? I gotta have another arrow on the other side, okay, to push it up, but then it would be twisting, then it would be going this way, it would be rotating. So what do? You add another line that's going the opposite direction. And so this right here, okay, this right here, what is that? This arrow on the top surface is going into the material. And so, you know, if, now let's just say that this is X coming out, the face, right? And let's say that we have Y going up. Well, X coming out of the face and Y going up, that means that this would be a negative. Like if assuming the magnitude of that arrow is positive, that would be a negative tau xy. Okay, because it's the X face, and it's going in the minus y direction. Okay? And that's interesting because this would be a y face and going into the minus x direction. Okay? So just like we said before, tau xy is equal to tau yx, right? We only have 6 in an isotropic homogeneous material. We only have 6 parameters that go into the state of stress. Right, that tensor, even though there are 9 slots, there are only 6. Tau xy is going to be equal to tau yx, okay? And we're seeing that right here. And this is just rotating this element and then looking at this face. Like so we're now looking at this face of this element right over here. Any questions on this? This is kind of important to be able to visualize this. You may not think, you're like, oh, I can, then at this point, everyone realizes the math for this class is not hard, okay? It's mapping the math to the geometry, to the loads, to the systems that is the tricky part, okay? All right. So like we said actually, this is a little bit out of order. Hold on. This is like we said here, okay? This is how you think of the cross section. This is how you think of the profile of the shear stress. So the shear stress is max on this neutral axis, all right, which is also on the longitudinal axis, or it's on. Yeah, that's where it gets tricky. That's on the same plane as the longitudinal axis, which I guess, depending on which book you're using, if it's neutral axis or longitudinal axis. But anyway, when y equals 0, tau max happens, and that's equal to 3/2 times tau av. Okay. What is tau av? Tau av is just the v that you would calculate from your shear force and bending moment diagrams, and A is a cross-sectional area. Right? You can kind of see all this mess is coming together. We spent a lot of time in statics drawing these shear force and bending moment diagrams. Then we spent a little bit of time learning different ways to draw these bending moment and shear force diagrams in this class. And now we're saying, I can tell you what the stress is if you tell me what the shear force is. Or the shear stress, yes, Matt.
Is transverse shear stress and normal stress the same thing?
No. No. Why? You tell me.
Well,
Okay, so what is a normal, this is where we gotta, okay, let's get back to some fundamentals. What is a normal stress?
stress that acts perpendicular to the cross section.
Perpendicular to the face, okay? So a normal stress has to be coming out of this face, or one of these faces, right? And there are 6 faces on the cube, right? But only like 3 pairs. You have the x face, the minus x face, the y face, the minus y face, the z face, the minus z face, right? So these arrows, okay, for lack of a better word, these arrows attributed to the shear stress, they're acting on the way I said it a minute ago. If x was coming out, let me just draw. I'll just make a messy mess, right? So if x is coming out like this, see that then it adds like a stress. I don't like that. Let me see if I can. Sure, right? Let's just say that. Oh, what did I just do? Yeah. Okay, so if I have, that's x, and that's y. Okay, you see that? This shear stress is acting on the x face. Do you agree? On the top line, these pairs, or this combined 4 arrows, are acting on an x face and a y face. You see that? But they're acting parallel to those faces, so they're shear stresses. All right. Now, what is transverse? Transverse is where things get a little bit okay, because I think different people actually think of it different ways. One person will say, oh, x-axis is the longitudinal axis of the beam. Okay? And therefore, transverse means across x, which is what v is. Okay? Right? V, I would say a V is operating transverse. Like, I'm not a doctor or surgeon, but they have like their different views of transverse. I don't even know, sagittal, whatever. They have those different different perspectives, right? But this is a transverse perspective. Okay, so sometimes though you'll hear, so like I get confused. Like I drew transverse. I kind of indicated this one, but I could have equally said it's this one. Sometimes like Hibbler, even I get confused reading some of this stuff. Not even I. That sounds arrogant, but they'll talk about the transverse shear stresses, right? We talked about the different laminates. If you watch the videos, there are these different laminates, and so if they can slide against each other, or the idea that they're sliding against each other, that's associated with a transverse shear stress. Okay? So transverse to what? I don't know. Transverse to the normal load that I'm applying to it? You know, you can think of it different ways, but they're the same. They're same magnitude, right? And because it's an isotropic homogeneous material, they are going to tau xy is going to be equal to tau yx, right? So do you see that this is technically the way of drawing things. This is technically tau xy. Okay, the way we've drawn things here, okay, because it's on the x face, it's going in the minus y. So maybe technically you could say it's like it depends on how you want to define it. It's like a negative. Okay, maybe let's do it this way. It's a negative tau xy. All right, because at least it's going to be negative in that quantity. And this is where it's useful to have a number. Like if they say that it's negative 1 megapascal, right? Then you're like, oh, okay, so tau xy is equal to minus 1 megapascal, the way it's drawn here, okay? But this is also kind of equal to tau x minus y, right? Because this is in the minus y direction, okay? Or I guess I would say that's, no, this is right. Minus tau xy is equal to that. Okay, so actually no, it's so tau x. So it is. So this would be a positive. So tau xy. Yeah, see, I get confused. So I would say that this is like if I said 1 megapascal, then I would say okay, I could also write tau x minus y. Okay, so I guess this is. Yeah, it's just, it goes back and forth. So the point is, we got to know the face and we've got to know the direction it's going. All right, and I'll erase that to avoid confusion. Okay, and then if it were circular cross section, then it's 4/3 tau average. That's how you figure out the tau max. Usually with shear stresses, okay, except for later on in this session, we got to get through this. Okay, I'm running out of time. You don't care too much about the positive or minus signs, but you'll see in a minute when we have circular cross sections, you can apply torsion and shear that they add up, or they subtract, or they work. Yeah, they work with or against each other. So, for example, maybe it's best if I say this right now. You see that we can figure out the direction of the shear stress here on this torsionally loaded thing. Now, let's say that this is x aroni. Okay? And let's say that this is y. Okay? Right? That kind of corresponds to what we had here. Now, if I pick an element right here, like on the outskirts, okay, and I'm looking, that element is actually looking into the face. Okay, so if I pull that element over here, okay, can you see this? Right, this is the element. Like that. Okay. So this torsion is contributing a shear stress like that. Any question on that? That's true, right? And then there's going to be another shear stress that goes like this. There's going to be another shear stress that goes like this, and there's going to be another shear stress on the element that goes like that. Okay, because that element has to be in equilibrium. Okay. But now here's the kicker wicker. What if I applied a force externally like that on the end of the beam? That's like what I have over here. Okay? Well, it turns out if it's at the end of the beam, okay, it's a bad example. If it's at the end of the beam, it's so hard to make a good example. If it's at the end of the beam, then the then the shear force that I draw when I take that slice, right, it's going to be going downward, and so it's going to be anyway, it's going to be like negative of it, right? So it's like it's kind of confusing which direction to do it. My point is that let's just say, better said, there's some magical shear force V, okay, from bending. All right, just some magical shear force. You see, this max right here will be at the longitudinal axis. So this from bending will result in a shear bending that's equal to what? 4/3 V over A. Do you see that? Because we just said that from bending, it's a max at the middle. And if it's a circular cross section, then it's 4/3 tau average. And this comes back from width. Okay. So now, if I've got that situation, I can add T, C, and J to 4/3 over VA. Does that make sense? So I'm combining the shear stress from bending with the shear stress from torsion. Why? Because these are actually it's not adding, it's subtracting. Right? Because this shear stress is up, this shear stress is down. So it's actually the combined would be again, I'm trying to keep things straight. This is the way this is, yeah, this is going up, this is coming down. So if that's x, so this is going to be, so tau x y, okay, would be TC over J minus 4/3 V over A. Okay. Because they're acting in opposite directions. Questions on this? Yes?
The torque bending equals 4/3 V over A. What kind of
The shear stress from
shear
bending,
stress?
not torque.
Torque.
Right, the shear stress from bending. Yes, go ahead. No, keep asking your question. I'm just making a minor correction.
That sort of helps to explain it. So you're basically saying, what is the proportional? What is 4/3 times tau average? What is that torque bending? Or not torque?
Was that shear stress?
Yeah.
That is the maximum shear stress at or along the neutral axis.
Okay, so it's torque max.
It's shear stress max.
Sorry, my high school teacher used tau for torque.
Sure, yeah, that's fine. That's fine. It's just, yeah, I agree. We use tau for time constants and for differential equations. No one has a corner on the market of these Greek variables. Okay. So So the point is that this is in the same direction, right? This on the same face at the same location, and so we can add them to each other. Okay, so now that we've done that, I spent more time on that than I normally do, and we were running out of time for the class. That clock is super slow, right? Do we agree? Or like 4 minutes slow? Okay, yeah, so I'm like confused. I'm like, look at this clock, look at that clock, like what's going on? All right, so here, let's do this. I think, what I've said here is maybe a little different than what I've said in the other videos. So like, you can watch the videos to catch, because I focus more on these problems than on the, or more on these examples in the videos than maybe I have time to do here. But I've also spent more time now talking about how you set things up, more generally speaking. Okay, so here we have a circular beam or shaft, okay, and it goes around the bend. And these are like the worst problems, okay? That, I mean, what's worse is like if it goes around two bends, okay? All right, just around the river bend. That is Pocahontas, I think. All right, someone has kids. All right. So here, what are we gonna do? We're gonna draw the cross section at A, and I think what's often useful to do is draw it multiple times. Okay, and what do I mean by that? Often it's useful to draw it like one time per load that you're considering. Now, in this case, I probably was repetitive. So that, like, I drew it once. This is just to give you the idea. Okay, but you'll see near the end of the notes, if you watch the video or you look at the notes, I like draw it like 3 times because there are like 3 different loads that I'm considering. So in this case, what is the load that is of interest here? And actually, I'm kind of lying. This load does 2 things. So actually, I'm right. I have 2. Sorry, I have drawn it twice for good reason. Okay, but not for the same reason I draw it at the end of the video. Anyway, okay, let's just draw them both here. What are the 2 loads that this thing is experiencing? Yes.
You got the torsion thing, it's P times A.
Yes. That's one. And there's another.
So the bending.
Yes. How did you get that?
Because of the, like, you get the length and then you see how it's turned, so you get the A also.
Yeah. So what you're saying is, if I move P over to here, right, which you can do, you move it over there. So now it's no longer contributing this torque, but it's over here. It can be pushing up on this end, and that would be causing it to bend. So if it's bending there, okay, then I can have transverse shear stress. Okay. And that transverse shear stress is going to be essentially from that P pushing up. So that P is acting up, and if I were to take a cut, a slice, I could, and I drew it opening to the left, okay, I would actually draw V upward as well. Okay.
So does that mean you have to do 3 separate equations? Or?
So, not, I mean, I guess the number of equations maybe is questionable, but there are 2 quantities, right? I've got a quantity from the P being the internal shear force, and we've got this other quantity, which is going to be giving us the shear from the torque. Okay. So what do we have? We have a torque or a shear stress. Now I'm doing it. A shear stress, okay, from the tau average, from P being essentially like making a fictional P here that's acting up. And we've got shear stress, okay, from the torsion. Okay, so this is how we think of this one. This torque is coming around here. The torque from the shear stress, or the shear stress from the torque, is going to be max at the outskirts. So that's going to be a TC over J quantity, right? So this tau T, we'll call it from the torque, is TC over J, and it's acting in the same direction as the P, as I've drawn here. Okay? And so in that case, I can write J is that, and the total tau, the total tau is going to be adding these together. Okay? Like that. Okay? Questions? So, the point here is that you can have different types of loading that create shear stresses, and if we can figure out where they are at the same location in the same direction, we can map them together. Okay. There's a question that you get to answer there. The last part, okay, which I can go through kind of quickly, is what happens when you have normal and shear loads. Okay, and this is where I said you get to draw multiple diagrams in some cases. All right. This one is simple, okay, in that I've got a normal force and I've got a shear stress that's induced from Tap, okay? And now when I draw the diagram, okay, I've got normal stresses coming out of it and I've got shear stresses going around it. Okay? And you can, if you want, you can watch the video to get more of an explanation to do that more quickly. Okay? And then here, for this type of situation, I've got now 3 normal forces acting on the end of this beam, right? And they can have, I can move them. So one is they induce torques, right? And now I'm saying, okay, this is a distance A from the end, okay? Because I got to be specific about the amounts of torques. And that also I can move these over here, and then they can act like shear forces, or they create shear forces along the beam as well. So each one of these is creating a shear force. Well, actually, no. This is creating a shear force. Yeah, this is creating a shear force. This one actually is not. PX does not, because if I move it over here, okay, it would be acting here, so it would be creating a normal force at A. But all 3 of them are creating torques. Okay, at A. But then it becomes a matter of, okay, which directions are the shear stresses that are being induced by these torques, or which directions and what are the magnitudes of the transverse shear stresses that are happening because of it acting like a beam. Okay, and so for this, it's pretty complicated, but here it's good to draw out, okay, the contributions from the different forces. So in this case, we're drawing a cross section here. You see this is X coming out, so this X coming out Y at the top. So this is that pizza that's right here. And we think about contributions from PX. So we're only going to think about PX. PX is inducing a torque, right, that's going to be causing this to kind of go this direction, right? See that? So that torque, or that moment that's induced this direction, would that put A, is that going to put A in bending? Yes. Is it going to put it in compression? Yes, because it's above, right? So you see that PX is going to cause a bending, which is going to cause it to smile, and it's going to put that top region in compression. PX will also induce a normal stress. So if I move it to this fictional spot, okay, here along the x-axis, you see that it's pulling it out. It's pulling and it's causing a normal stress. Okay. And then if you see here, PY is going to be causing a torsion, a twist, right, where the shear stress goes down. And it's also causing a bending, okay? But it's causing a bending that will, you see, like PA is the moment, but, and it's at the neutral axis. So neutral axis, if you're at the neutral axis and you're bending, then your bending stress is 0, okay? But then PY also can be moved over here, and it causes the induction of a transverse shear. Okay? And transverse shear stress all right, is maximum when it's on the neutral axis. So you have to account for it, all right? So what you do is you do all this accounting for these different, no bending stress because it's on the neutral axis, but yes, there's a transverse shear stress here, all right? The V standing for the shear force, and there's also a torque, all right? And then the similar thing happens with PZ, all right? This is hard stuff, all right? This is hard to visualize, okay? And so it's very important to go piece by piece by piece. Any questions on this? Okay, go through it more slowly, all right? And you'll get a chance to do it on homeworks. Of course, if you look at some of the extra notes from fall of 2023, as you saw, some of these things are worked out for you. Nonetheless, it's important to get an idea of what's what. All right, I'll see you tomorrow. Some of you probably early, some of you at 1. It's your choice. Thank you.
When are the exams posted? Because I didn't actually know that they were posted.
Hold on a sec.